Thank you. Good morning, everyone. It's my pleasure to introduce today's thesis presenter, Jayasri Nikitha Guthula, a master's student in the Department of Computer Science and a graduate researcher, a student researcher, I'm sorry, at the Emerging Analytics Center. Her thesis is titled Secure Frameworks for User Motion Data in Virtual Reality. Go ahead. Thank you.
Good morning, everyone. I'm Jayasri, and I'll be presenting secure frameworks for user motion data in virtual reality. So, virtual reality offers an amazing and incredible immersive experiences driven by detailed motion telemetry. But it tracks head movements, hand gestures, and spatial interactions. But there is a catch. Everything comes with a price. So in this case, you're essentially trading your biometric motion data for the for these experiences. And there is a real problem. This data is incredibly fine that with just 1 in a million users, we can pinpoint to who they are. So, and the traditional privacy method fails to protect the sensitive information. That's why secure frameworks are very crucial. Think about it. VR telemetry is not just a random set of numbers. It's continuous, user-specific, and very detailed. Even if we anonymize it, those unique motion patterns reveal too much information about the user. So traditional privacy methods fail in this case. What we really need are approaches that balance both privacy and utility. What you see in this diagram here helps you visualize the pipeline of privacy exposure. First, devices like head-mounted displays and controllers continuously capture the motion data. And this data tracked is real-time and creates detailed movement logs. Over time, these logs form a unique motion pattern, essentially a behavioral fingerprint. Even without usernames or IDs, these patterns can lead to identify patterns and identity exposure. So our goal is twofold. First, to protect user identity in VR systems, and second, to preserve the analytical utility of motion telemetry for feedback and VR experiences. This is a challenge because every movement in virtual reality, whether it's a head tilt, a hand gesture, or controller input, encodes user unique behavior traits, making it much more identifiable than traditional data forms. So the real challenge is balancing utility with usefulness, as protecting privacy often reduces the richness of the data. In short, the question is, how do we keep this data useful for feedback as well as analytics while ensuring it doesn't compromise the privacy of the user? So there has been significant progress in privacy preserving techniques such as anonymization, synthetic data generation, differential privacy, and homomorphic encryption. These methods have proven effective in securing structured data sets across various industries. Anonymization and aggregation helps protect privacy in traditional data sets, while synthetic data generation preserves structure without exposing real records. Differential privacy provides robust mathematical guarantees against data leakage, and homomorphic encryption enables computations without decrypting sensitive data. This thesis leverages the state-of-the-art methods to address privacy concerns in the dynamic and high-frequency world of VR telemetry. Here is the gap. No one has empirically tested privacy solutions on real VR motion data. Existing synthetic models lack sequence realism and leak resistance. Most encryption work has focused on static data, not the high-frequency telemetry inputs we see in virtual reality. There is also no established benchmark for evaluating the privacy utility trade-off in immersive environments. So finally, existing methods haven't been validated in real virtual reality contexts. The research objectives are pretty straightforward. Assessing re-identification risk by evaluating the extent to which raw telemetry can be linked back to individual users using similarity-based metrics, generating synthetic data using Wasserstein GAN-GP trained with DP-SGD to retain statistical structure while enforcing privacy constraints, implementing encrypted analytics using CKKS Homomorphic Encryption to enable secure computation on scalar motion features. Evaluating privacy utility trade-offs by benchmarking each of these two frameworks across analytical performance, privacy guarantees, and runtime efficiency. Now, why is anonymization such a problem in virtual reality? It's simple, because motion data is essentially a behavioral fingerprint. Locke et al. Have showed this as early as in 2003 with physical interaction patterns. There are also studies that demonstrated re-identification using just motion traces during a 360-degree video playback. Recently, they used, Nair et al. Used machine learning to match user sessions based on head and hand motion patterns. These findings confirm that anonymization alone is insufficient. The identity is in the behavior, not the metadata, and that more robust frameworks are required to protect privacy in immersive systems. In fact, as you can see here in this slide, the motion data can reveal a lot more than just identity. It can infer things like sex, age, height, handedness, and this means that we need to rethink how we can handle this data, and because it's not just about protecting identity, but it's also preventing other personal attributes from being inferred. Yes, so as you can see, these are attributes and their accuracy rates from a study by Nair et al. So for this, to test these ideas, we are using the Boxer 23 dataset developed by Berkeley RDI. It is a large collection of real-world telemetry captured from GAN Beat Saber. There are a few reasons why this dataset is ideal. It's high frequency, capturing motion signals with fine temporal granularity. It also reflects natural gameplay, not scripted lab scenarios. So it's a representative of actual virtual reality user behavior. And it also contains a variety of users, which helps test the generalizability of these privacy methods. And this dataset allows to experiment in conditions that mirror real deployment, making the evaluation more meaningful. Before we dive into the privacy frameworks, the data needed some cleaning. So I normalized these features, clipped outliers, and grouped the data into fixed length chunks. This step stabilizes the data for a model training and ensures comparability across users. Here are the two frameworks. First, synthetic data generation with Wasserstein GAN-GP and DP-SGD. It replaces the raw data identity. And the second framework is to encrypt computations via CKKS, which allows us to analyze real data without decrypting. Each framework is an approach to secure user privacy at the data generation level and also in the analysis level. The first framework, with synthetic data generation, I used WGAN-GP trained with the DP-SGD. This approach replaces the raw telemetry with privacy-preserving synthetic data. The challenge here is to make sure the synthetic data is realistic and it can be useful for analytics, which also ensures, ensuring that no one can re-identify the user from the generated data. Here is how it works. We pre-process the data first and then feed it into the WGAN-GP model, which generates synthetic data. The DP-SGD technique ensures that no single user's data dominates the learning process. After that, I validated the synthetic data using statistical tests to ensure it behaves similarly to real data without leaking the identity. The second framework applies CKKS encryption to telemetry. This allows us to perform computations like averages on encrypted data and without ever decrypting it. So it's a great way to analyze sensitive data while keeping it secure. So here is how the encryption works in practice. The telemetry is encrypted using the public key computation, and the computations are performed blindly, and the result is decrypted with a private key. Gauba key allows operations on encrypted vectors without ever exposing the raw data. So to present it in demo, like I have a demo to show how we can do it in real time. So here's a demo. So this demo, it's about it's a small virtual reality experience where we have a table with 3 spheres, and as I interact with the spheres, my motion data is being tracked in it, and we use LStat to store the tracked data, and then we perform homomorphic encryptions to compute the statistics on raw telemetry data as well as the encrypted telemetry data. As you can see here, it's very simple, basic. Okay, where I use my fingers to pick up balls and like just move them around. My motion is being tracked right now, and as I quit the game here, our motion data is captured. So I'm going to run this application. So the raw statistics and the encrypted statistics are here. Let me show you the summary files of this, because it's easier to understand. So as we can see, the raw the encrypted time, the statistics are real. Like the raw time and encrypted time have the same values, which means we can run the analysis on encrypted data without losing its properties. And so implementation highlights. So the project uses 8 RDX 2080 Ti GPUs and LXT containers for data processing, with over 100 hours of training on complex beat saber gameplay scenes. This also to test the privacy preserving methods as well as under real high-speed conditions. These evaluations and results, the results are strong. So we have raw telemetry had 100% re-identification accuracy, but with synthetic data, this dropped to 0.04%. I used kernel density estimation to show that the feature distributions were preserved, and KS tests were also confirmed that there was no significant divergence in statistical properties. As well as additionally, encrypted computations had less than 0.5% error post the decryption. So the results are promising, but there are still some limitations. Some features didn't fully replicate real data statistics, real data distributions. Large-scale training faced challenges due to the complexity of Wasserstein GAN model, and the encryption setup had limitations such as ciphertext expansion and vector packing, affecting the scalability for temporal analytics. To conclude, virtual reality motion data is highly identifiable even when anonymized. Synthetic data generation successfully prevents de-identification at a scale, and encrypted analytics allows us to compute securely without revealing any sensitive data. These methods offer a very clear path towards secure and private virtual reality telemetry analysis. Looking ahead, there's a lot more to explore. We can extend this work to surgical, industrial, and collaborative virtual reality environments. Integrating temporal models could also improve motion sequence realism. Plus, developing real-time encrypted analytics will open up new applications in low-latency VR systems. This is the end of my presentation, and thank you very much for your attention.
Thank you, Jayasri.